Today we're going to go into some things, some additional stuff in Chapter 4. We're going to start with inverse functions. Inverse functions are functions that let you go back and forth between domains and ranges, essentially is what it amounts to. We've looked at what functions are. Functions are relations that have one output. If you have an input, you have only one output. You can't go to two different outputs. Now we're going to look at something called one-to-one functions. So there are a function, but they're going to have an additional restriction besides just being a function. A one-to-one function is one such that for every output, there's only one input. We didn't have that restriction on a function. We had a restriction that you couldn't have two arrows begin from the same point. Now we cannot have two arrows end at the same point. So here is an example. Okay, here's a domain and a range. This is a function because we only have arrows beginning from one point. We don't have two arrows beginning from the same point. The fact that we have two different beginning points going to the same end point is okay to be a function. But it's not one-to-one because we have two of them ending at the same. What it takes to be one-to-one, it first has to be a function, and then it has to also satisfy this condition that there's only one arrow coming into a point. The reason we do that is we need to be able to move back and forth in either direction without any ambiguity. If we're here just with a function, we can move from left to right and there's no ambiguity. But if we tried to go from right to left, we wouldn't know for this number 7. We wouldn't know where we would be winding up. So you need this situation. If it's an arrow diagram, the arrows begin at one point, end at one point. There's only one coming out of a point. There's only one going into a point. That is a one-to-one function. This is the sort of thing you look for if you're looking at an arrow diagram. That's the same thing that this says in mathematical terms. That if you have A and B in the domain, then if A is different from B, so if you have 1 and 2, then these must be different also. What that means is you can't have two of these starting and going to the same one. That's what this says in equation form rather than just the diagram. So that reverse direction would not work for us. If you're looking and trying to decide whether a function is one-to-one, let's start all the way back at a relation. First, you need to decide if it's a function. If we look at these first elements, they're different, so it is a function. So next, we need to look to decide whether it's one-to-one. For ordered pairs like this, you do the same kind of thing, only you do it with the second ones. So to be a function, the first ones all have to be different. To be a one-to-one, the second ones all have to be different. One-to-one requires both function and that the second ones be different. So -3, 1, 2, that is a one-to-one function. And just like for when you're deciding if it's a function, if you have a repeated second element, the only way it can be one-to-one is if the first elements are repeated. So this would only be a one-to-one function if both of these were either 1 and -3 or both of them were 3 and -3. That's the only way it could be one-to-one. Either the second ones all have to be different, or if they're the same, then the first elements have to be the same also. Same sort of thing that you had to be a function. First elements have to be different, or if they're the same, the second elements have to be the same. It is a function, but it's not one-to-one. But the reason that this is necessary for what we're doing now is when we have a function, we want to be able to put an input in and always get the same output. For an inverse function, we want to be able to start from an output and always get the same input. So we want to be able to go in the reverse direction and always wind up at the same place. Graphically, similarly to the way we have the vertical line test to test whether it's a function, we have a horizontal line test to test whether it's one-to-one. Same concept. If a horizontal line intersects the graph in more than one point, then it's not one-to-one. Or this says if it intersects no more than one, then it's one-to-one. So here's an example. This is a function. It passes the vertical line test. But when I draw a horizontal line, it's intersecting it at more than one point. Therefore, this is not a one-to-one function. This one is a function, passes the vertical line test. I can pass horizontal lines anywhere I want. It only intersects once. Therefore, it's also one-to-one. You could have a curve, but it can't double back on itself. For instance, you could have, like the cubic, that's one-to-one, because it never comes back down. It always keeps going up. So you can have curved lines. A parabola is not one-to-one, because, it's U. So any horizontal line is going to intersect it more than once. So if you're trying to decide if a function is one-to-one, if you can find two different values of the output of the function, or I guess they're saying it another way. If you have the output of a function is the same for two different inputs, that means the inputs have to be the same. If you can show that, then that shows that it's one-to-one. This is hard to do. We're not going to do much of that, if at all. The best way on something like that would be probably to go ahead and sketch a graph and see if it doubles back on itself, rather than trying to work with it from the equation perspective. The equation is more difficult. If you can remember certain things like the even degree polynomial functions are not one-to-one, ever. The odd degree may be, they may not be. Straight lines, unless they're horizontal, they are one-to-one. So the horizontal line, you draw a horizontal line there and it intersects more than once. A vertical line is not a function, but anything else is a one-to-one function. So if you can find two x values that produce the same y value, then you're not one-to-one. Because if you think back to the arrows, that's one that's not a one-to-one function. If you can find two x values that produce the same y value, that's when you're trying to work with something like this. Sketching the graph is probably easier, and then use the horizontal line test. The horizontal line test is easy. If you know that it increases over the whole domain, then it is one-to-one. Like the cubic function, we know it increases over the whole domain. Okay, so we're leading toward inverse functions, and inverse functions require this property of being one-to-one. Because the idea of an inverse is to go back from where you started from. And that's what we're going to do with these inverse functions, is we're going to start here, use a function to get here, then the inverse function takes us back to where we began. And that's why we require that 1-to-1, so that we get back to the same starting point. You can think of that as the inverse undoing the original function. Here are two functions. We can test whether they're inverses of one another. If we put the number 4 into f, we get the number 37. If we take the number 37 and put it into g, we get the number 4 back. So essentially applying both of those in sequence gets us back to our starting point. We started at 4 and we wound up at 4. So these two, at least for that number, are inverses of one another. I gave you a 4. We're going to look at it in a more general sense. This is the idea, though, is that if you take a number and apply one of the functions, and then whatever that result is, you apply the other function to that, if the combination of both of them gets you back to the one you started from, then it's an inverse. They are inverse functions. That's the idea. Mathematically, it boils down to being this. So you're going to take one function and evaluate it, use that result as an argument for the other function, and if that takes you back to the starting point, then they're inverses. And if you recognize that, that's the composition function. That's the composition operation, where you're taking a function of a function. It works in both directions for inverse functions. F of g of x equals x, and g of f of x equals x. If that's true for all x, then f and g are inverses of one another. This is the requirement, that this gives x and this gives x, no matter what x is. You can sometimes find a pair of functions that work for a single number or a few numbers, but to truly be inverses, it must work for every number. So if f is a 1-to-1 function, and that's a requirement that it be 1-to-1, it be a function and it be 1-to-1, then if g is an inverse, it must be true that the composition f of g gives x and the composition g of f gives x for every x. That's the mathematical statement of what an inverse function is. So if you have a function that's not 1-to-1, then it's not going to have an inverse, because you can't guarantee you'll get back where you started from if it's not 1-to-1. That's the concept of 1-to-1. You get back to the starting point. So anytime you're trying to find an inverse, your first check would be to see if it's 1-to-1. If it's not 1-to-1, you can stop, because it does not have an inverse. Let's suppose we have two functions. They look like possibly they could undo each other, but is g really the inverse of f? Is f really the inverse of g? Let's check. That's a straight line with a slope of 2. You should be able to recognize y equals mx plus b. Slope is 2. Y-intercept is 5. This one is a straight line with a slope of 1/2 and a y-intercept of -5. And I said a minute ago, but I'll say it again, straight lines are 1-to-1 functions, unless they're horizontal or vertical. But any other straight line is a 1-to-1 function. So they're both 1-to-1 functions. Therefore, they do have inverses, because every 1-to-1 function has an inverse. If it's not 1-to-1, it does not have an inverse. So they have inverses, but are they inverses of one another? If you perform the composition operation on those two functions, and if we get x back as a result, then they are inverses. So let's take g of x and plug it in there. G of x is 1/2 x minus 5, and I need it to be true at every x, so I plug it in as the expression, not as a number. I plug the expression into f. If I plug that expression into f, what that means is I'm putting 1/2 x minus 5 right there, which means I'm doing this. And if I do that calculation, I get x minus 5. X minus 5 is not equal to x. Therefore, those are not inverses. They're close, but x minus 5 does not equal x. It must equal x. So those are not inverses of one another. They do have inverses. They are inverses of other functions, but not of each other. The notation that you use to indicate an inverse of a function is this exponent of -1. This is a situation where you do not interpret that to mean 1 over f. Normally a negative exponent, you deal with it by flipping it over. This is an exception. This is the notation used when it's used with a function name. It means inverse of the function. It does not mean reciprocal. It means inverse of the function. So this is f inverse of x. And that's the way you say it, f inverse of x. Function notation. Because we're doing inverses, if you think back to those arrow diagrams, the domain of f has this range over here. But we're coming back the other way, so this thing over here is the domain of the inverse. In other words, the domain of the inverse function is the range of the function itself. And the range of the inverse function is the domain of the original function. So the domains and ranges just flip-flop. The domain of one is the range of the other when you have inverses. So we looked at a pair of functions and checked whether they were inverses, and they were not. How do you determine what an inverse is? Well, if you have a set of ordered pairs, the way you do it is just by flipping the order of the two numbers. In every pair, switch the order. So if you have the function g, and it is a function because I have no repeated first elements, it's 1, 2, 3, and it has no repeated second elements, so it's 1 to 1. So I have a 1 to 1 function there. The inverse of that is to switch the pair. So instead of 3, 1, I'll get 1, 3. Instead of 0, 2, I'll get 2, 0. So just in every pair, switch the order. And this is the inverse. And notice it's written as G inverse of the numbers. So the inverse of a set of ordered pairs is just switch the order of the pairs, of the numbers in the pair. Very simple. Here's another one, F. When you're checking for inverses, the first thing you should do before you try to do anything else is make sure it's a 1 to 1 function. -2, -1, 0, 1, 2. So it's a function. 1, 0, 1. Oops, I've got 1 repeated. And the -2 is not repeated, therefore it's not 1 to 1. Turns out I also have 2 repeated, and that the 1 and 2 are different. So that is not a 1 to 1 function. It is a function, it's just not 1 to 1. Because of that, it has no inverse. So don't waste time trying to do anything with it. It does not have an inverse. What if it's not a set of ordered pairs? What if it's an equation? Well, here's the technique. And instead of writing f of x all the time, because that's a lot to write, I'm going to use y instead of the f of x. Take your function and interchange the x and y's. Wherever there's an x, write a y. Wherever there's a y, write an x. So interchange the x and the y. Solve that equation for y. And then wherever y is, put f inverse. And that's the inverse. So here's an example. Here's a function. What's its inverse? First thing you want to do is check, is it 1 to 1? You have to remember now what that looks like. What does the absolute value function look like? It's a v. It's a function. We know that because it passes the vertical line test. Does it pass the horizontal line test? No. So there is no inverse for that one. What about this one? Is this one a one-to-one function? What shape is this equation? If I drew that graph, what would it look like? Did you recognize that form? Y equals mx plus b. What does y equals mx plus b look like? Straight line. Anytime you have x only to the first power, when the only exponent on x is 1, it's going to be a straight line. What else do you know about that straight line? Slope 4, so it's going up 4. It crosses the y-axis at -7. So I've got a line like this. Is that a one-to-one function? Yes. It's a straight line, therefore it is. Because it's one-to-one, it does have an inverse. So now we can go find that inverse. But don't waste time to find an inverse until you check whether it has one. Okay, now that we know it has an inverse, what we're going to do is instead of continuing to write g of x, we're going to put y here. And we're going to say y equals 4x minus 7. Then we're going to switch the x and the y. And so I get x equals 4y minus 7. I'm going to take this second equation now, and I'm going to solve that equation for y. So add 7 to both sides, divide both sides by 4. And you get this. Now for the y, I'm going to replace it with g inverse. And so g inverse of x is 1/4 x plus 7/4. What that means is that if I do the composition of g of x and g inverse of x, I will get x as a result. Let's show that. I want to do g of g inverse of x. So that means I'm going to do g of this. But if I plug this in here, that means I'm going to be doing 4 times 1/4 x plus 7/4 minus 7. I just plug this into here. Multiply my 4 there and I get x plus 7 minus 7, which equals x. So g of g inverse equals x. Therefore, these are inverses of one another. That's the requirement, is that if you do the composition, you get x as a result. From right there. But I got it from right there. What I'm doing is I'm plugging this into G. Well, this is G. I'm taking G of G inverse. This is G inverse, which means I'm taking G of this. So I'm plugging G in here. I'm plugging this into here, which means I plug that into here. So the 4 comes from right here. I'm just taking this expression and putting this in place of x. So the 4 was part of my original function. So take your function, write y instead of g, write y instead of the function name, interchange the x and y. Solve that new equation for y, and then replace y with the inverse name. That's how you do it. Okay, so here's another one. And whenever you're asked to find an inverse, your first thing you should check is the function one-to-one? And this is where knowing those basic shapes and what the effect of transformations does to that shape is beneficial. Because if you're asked, is this a one-to-one function? First of all, is it a function, and then is it one-to-one? Then, unless you just graphed it, it's going to be difficult to tell. But if you know the basic shapes of functions and what effect transformations have, then you can know what that is. Because here, what we have is we have the basic function x cubed with something added outside the function. The basic shape of x cubed is what? That's a one-to-one function. Passes the vertical line test, passes the horizontal line test. What does adding 5 outside do to that? It moves it up by 5 units. Therefore, it's still a one-to-one function. Therefore, this does have an inverse. So how do we find that inverse? First step is, instead of h, write y. So I say y equals x cubed plus 5. Let me go ahead and do it manually. Might be a little easier to follow. So I'm going to write y equals x cubed plus 5. All I've done is, instead of writing h of x, I write y. Then what? I want to take this and interchange them. So I'm going to write x equals y cubed plus 5. All I've done is, instead of y, I'm going to write x. Instead of x, I'm going to write y. Not really solving anything. I'm just renaming. Now I'm going to solve. I'm going to solve for y. So subtract 5. Take the cube root of both sides. And I get y equals the cube root of x minus 5. Now that I have y, I put the inverse name in. So instead of y, I'm going to say h inverse of x equals the cube root of x minus 5. And that's the inverse. We can verify it by taking this and substituting in there, or taking this and substituting in here. Either way, it should give us x as an answer. If I take this one and substitute the right-hand side up here, this is the cube root, I'm cubing it. That's just going to get rid of the radical, right? Anytime the exponent and the index are the same, it just erases the radical. So that gives me x minus 5. X minus 5 plus 5 is x. That's the process. Not difficult. You do have to solve an equation. Not a difficult equation usually for this type of calculation, but it could be any type of equation. Now at this point we've only looked at certain types of equations that we can solve. We know how to solve radical equations, we know how to solve quadratics, and now we've also looked at solving things higher level polynomial equations. But that's about where we stop. We're going to next look at some additional types of equations. But having this inverse calculation can be useful. If you're working on a problem, say a business analysis, and you have a certain response to some input, if you'd like to be able to determine what the input to that was, what defining function gave you that output, you being able to calculate an inverse is a way to do that. So say you take a bunch of data and you get a function to fit that. You can invert that and say, okay, given the input, what output should I expect? So this ability to find inverses is useful. In order to be an inverse, the function has to be 1-to-1. Also, if it is 1-to-1, then there is definitely an inverse. So if it's not 1-to-1, there is not. If it is 1-to-1, there is. The domain of the function is the range of the inverse. The range of the function is the domain of the inverse. Picture those arrow diagrams and just, domain, range, switch it as domain, range. That's the easiest way to keep it straight. And kind of like the ordered pair thing when we looked at it, if the point AB is on the graph of the function, then the point BA is on the graph of the inverse. It actually winds up that the inverse is the reflection of the original function, but now instead of reflecting across an axis, it reflects across a diagonal line. So if you have your axes like this, and you have a diagonal line, y equals x, then a function and its inverse are reflections about this diagonal line. So if you draw your function on here and then reflect it about the blue line, you'll get the inverse of it. We're not reflecting about an axis, we're reflecting across this 45-degree line. But that's the graph of the inverse. And if you want to find the function, the equation for the inverse, you follow the procedure we just looked at. You replace the function name with y, interchange x and y, solve for y, replace y with if inverse. Just like we looked at in the previous two examples. Let's suppose we have the function 1/2 x minus 1 cubed minus 1. What is its inverse? Well, your first question is, does it have one? And that's checked by doing the check for 1-to-1. If you remember the relationships for basic functions and transformations, this function is the only thing, all it is, it's the x cubed basic function that has been moved to the right. It has been squeezed down toward the x-axis, and it's been moved down. So none of those squeezings and movements change the basic shape. It's still that S shape, which is constantly increasing. A constantly increasing function is 1-to-1. So if you can remember those things about the basic shapes, the odd-numbered functions are 1-to-1. The even ones are not, because the even ones are all going to be U-shaped. Horizontal line's going to cross twice. But the odds are all S-shaped, and as long as it doesn't come back down on itself, which the basic does not, and this is just a basic that's been moved around. All functions where the highest degree is an even exponent will not have inverses. It's possible to have it where it's not the highest, where you will, because if you cube x minus 1, you get x squared in x terms. It's actually x cubed plus 3x, or minus 3x squared plus 3x minus 1. I remember that because of something we're not going to get to. So here's our function. So we know it's 1-to-1, therefore it does have an inverse. That's all you have to do, is if you can show it's 1-to-1, it has an inverse. So what is the inverse? Well, let's go through the process. If we replace the f of x with y, same thing. That's all I did was replace that with y. Now interchange the x and the y here. Now we're going to solve this equation for y. I solve that by adding 1 to both sides. I multiply both sides by 2. Then I take the cube root of both sides. Then I add 1 to both sides, and I have y equals. That then is, I claim to be the inverse of this. Actually, I should put f inverse there. Let's look at that. Here's my function. F of x equals 1/2 x minus 1 cubed minus 1. This was my f of x. That's this blue line right here. See the nice S shape? It's just been moved to the right and down, and then it's been squeezed toward the axis, but it's still that basic shape. So this is my basic function right here. This is the one I solved for, the cube root of 2x plus 1 plus 1. If you look back, that's what that was. That's this green line. And a point I want to make here that I didn't talk much about, but is important. This red line, the red dashed line, that's the function y equals x. Or in other words, it's a straight line diagonal with a slope of 1. All inverse functions are symmetric about that line. And if you look, you can see the red and blue lines are symmetric about that. So that's an important feature of inverse functions. They are symmetric about that diagonal line. So remember that they are symmetric about this line. Inverse functions symmetric about that diagonal line. Another thing that I didn't put much emphasis on, but it's also important. If you have a point that's on this f of x, that's going to be an ordered pair, right? That point is 1 minus 1, point A. If you take those two numbers and switch their order, that point will be on the other curve. And let me show you how that works. See those points there? I can change my location, and they're still inverses. So this is like, the inverse of ordered pairs. That's all it is. But one of them is on this curve, one of them is on that curve. Will always be true for inverse functions. If you know a point on one function, then just switch the order of the points, and that will be on the inverse. No matter which way you're going. If I know this one, I can switch the order and I'll have that one, so forth. So it's a definite relationship, works for all inverse functions. So remember the diagonal, and that if this point's on one, this point's on the other one, just by switching the order of the x and y there.